Hello everyone, I'm Alexander Armbruster and I will present a PTAS for a scheduling problem. This joint work with Lars, Rohwedder and Andreas Wiese. And the scheduling problem we were interested in is called minimizing weighted flow time on a single machine. So in our setting, we have given a set of jobs, in this example 6 jobs, and each job has a processing time Pj, which is indicated by the length of the rectangle. And each job has a release date Rj, which is indicated by the left boundary of the rectangle. And now we want to compute a feasible schedule. It might look something like this. So we start with the light blue job, then we preempt this job and we want to resume it later, and we do the pink job, then we do the dark blue job, resume the light blue job, maybe work a bit on the green job, then do the red job, finish the green job, and finally we do the orange job, and then we are done. So the objective function we had a look at is called weighted flow time. So the flow time of a job is the time between its release date and its completion time. And we have just one weight for each job, and we multiply the weight with the flow time and add it all up. And that's a very natural objective function because that's like the time you needed to do the job. And in general, this problem is NP hard because there's a reduction from partition to it. And this problem already has a very long history. So back in 2001, there was the first log p squared approximation by Chikuri, Khanna, and Zhu. 1 year later, Chikuri and Khanna presented a QPTAS for this problem if the input numbers are polynomially bounded. And that already indicates there might also be a PTAS for this problem, but back then there was not even something close in this direction. So the best was a log square approximation. And in 2007, there was a log W approximation, where W is the ratio of the largest to the smallest weight. And the first step in the really right direction for a PTAS was a log P approximation for the general scheduling problem. So Banza and Proust did not care about the objective function. They allowed every objective function which depends on the completion time of a job. Batra, Garg, and Kuma then had a breakthrough result where they presented their first constant factor approximation in pseudo-polynomial time. And we'll have a closer look at what they did soon. Feige, Kulkarni, and Lee then proved that you can assume that the input numbers are polynomially bounded by a reduction to the setting. And Rohwedder and Wiese then showed that you can actually improve this O of 1 factor to a 2 plus epsilon. Now let's have a closer look at this O of 1 approximation and also the 2 plus epsilon approximation. So it works the following way. You start with this weighted flow time instance, and then they reduced it to a geometric covering problem with rectangles and stuff like that. And they only lost a factor of 32 in this reduction. And then they solved the resulting instance with a constant factor approximation, which had like a quite big factor. So in total, this is about more than 10,000 probably. Rohwedder and Wiese then for the 2 plus epsilon approximation showed that you can actually, instead of this covering problem, use a different, more complicated covering problem so that you only lose a factor of 1 plus epsilon in the reduction. And then they showed that you can solve this resulting complicated covering problem with a 2 plus epsilon approximation algorithm. And our contribution is now that instead of this 2 plus epsilon approximation, we actually can solve this complicated covering problem optimally, which then of course results in a 1 plus epsilon approximation in total. But because this more complicated covering problem is complicated, what I will present today is how our algorithm works for this covering problem. So this covering problem is a bit easier to understand. And for that reason, I will explain how our algorithm optimally solves this problem instead of this, but from this problem to this problem, it's very easy to understand. So let's have a look at this geometric covering problem they observed. First of all, instead of computing an actual schedule, we only compute deadlines for each job. And we mark our deadlines by just marking
the time from the release date to the deadline in this image. So there's one row for each job. And if the second job is released here in the second line, we start at the beginning with blue rectangle squares until the job is finished here. And then we have white squares in the end. So instead of computing a schedule, we can also just select squares in this image, which has kind of the same meaning. But on the other hand, if we select squares in this image, we afterwards need to keep track, we need to check that there is actually a feasible schedule for the deadlines we just decided on. So we need to have a look for some constraints. Now suppose we look at this ST interval. There are 3 jobs released in this interval, and if we look at their processing time, it adds up to more than the length of this interval. So it's clear that at the end of this interval, there must be at least some work left because the interval is too short to do all the job. And that's what we will call the demand of this interval. That's the processing time that needs to be left over at the end of the interval. Or we can also phrase this differently. There are some jobs that have deadline bigger than t, and the processing time of those jobs need to add up to the demand. Because the jobs with deadline bigger than t are the ones we don't have to do until t, and that's the work we cannot do until t. So those are constraints that we need for if we select deadlines. And one can show that the constraints are actually sufficient. So if you have these constraints for each ST interval, then you can show using by applying earliest deadline first algorithm. I won't do it here, but you can show that you actually receive a feasible schedule if the deadlines fulfill these constraints for every interval. So now let's have a look how this corresponds to our previous image. Our constraint is that if we have an ST interval, there must be jobs with a certain processing time having deadline bigger than t. And jobs having bigger deadline than t is just the same as having a blue square here on this ray. Because if the ray is at t plus 1/2, deadline bigger than t means that the blue rays go somewhere to the right, and so the jobs that are not completed in this interval have this blue square here. So instead of having these constraints in this setting, we can also have these rays. And we have this demand for the interval, so we say that we have a demand for the ray. And this demand says that you need to select jobs here with a certain amount of processing time, namely the demand of this ray. Now the second problem that we have when we want to solve this resulting problem with a dynamic program is that we have these precedence constraints. So I said that we take all squares until the completion time. And that's kind of annoying because that's not very local, and local is better for a dynamic program. So we want to split up those squares into groups of exponentially growing length. Like in this example, we do that for all of the jobs. And now instead of selecting blue squares starting from the left, we just select rectangles, and we always select all squares in a rectangle or none of the squares. And well, the cost of a rectangle is just the number of small squares in it. And it turns out that because the rectangles get exponentially longer from the left to the right, actually this loses only a factor of 32. And if you do some more complicated tricks, including random shifts and stuff like that, you can show that you can also modify the problem a bit to only use a factor of 1 plus epsilon, as Rohwedder and Wiese did in their previous paper. So these rectangles are on one hand exponentially growing in length, which allows us to lose not a big factor when we do this. And the other important property of the rectangles is that they are aligned in a certain way. So if there's one rectangle here, for example, there's no rectangle partially below it. So if there's a rectangle ending here, Then there's also a rectangle here, 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 and here. So we get a tree-like structure where each rectangle has some rectangles below it, but nothing partially below it or something like that. That is super important for the dynamic program later. So we can actually forget about all the small squares and just care about the rectangles. So maybe let's do a quick recap about what we actually now have observed as a reduction. We have given a set of rectangles with these special alignment properties. And each rectangle has a weight, which is like the weight of the jobs times the number of small squares it originally was. And each rectangle has a size, and well, I would call it a size, but it's just the processing time of the corresponding job. And we need to have those demand rays. Each demand ray has a demand. And we need to select rectangles in this area, whichever we want, such that we cover the demand by the size of the selected rectangles or the processing times of the jobs where we select a rectangle add up to the demand of the ray. So that's the resulting problem that we want to solve. And in general, we want to use this tree-like structure. So we might to select rectangles in a certain area and then do a recursive approach to solve this problem. But suppose we want to select rectangles in this area. In general, that looks like a good area, and we will later do exactly this. And there's one big problem when we select rectangles in this area. So of course, we want to select rectangles with a minimal weight. But there's are those blue rays, and if we select rectangles here, we need to know how much of the rays we covered up here, because, well, they have a demand and we need to cover it, and if we don't cover it up here, we need to cover it in the hatched region. So in some way or the other, we need to keep track of how much of the blue rays is already covered. And yeah, so there's also the main difference to the previous papers, how we do that. So this reduction was the same as in the O of 1 approximation. And when we actually observe a PTAS, it's the same as in the previous 2 plus epsilon approximation, but the dynamic program to solve this is different. So the previous approach was to guess which rectangles, or to remember which rectangles are selected up here by including this in the DP cell. And of course, there you can only have a polynomial number of DP cells, so you kind of need to show that you don't actually have too many options for the rectangles up there, and it's really not clear how to do that, and the methods to remember them are also very complicated in the end. And we will do something completely different to remember which rectangles we selected up here. And for that, we really need the special structure of the demand rays. So I already told you how the demand of a ray is defined, and we can just have a closer look at the setting. And there are, of course, lots of rays that I didn't draw, but they might also exist. And I also computed all the demands for the corresponding rays. And so the previous papers never used the special structure, and because we used the special structure, we are able to observe a PTAS, which is the best you can get, as the problem is NP hard. And what you can see if you look closely at the demands is that the rows actually always differ by a constant. So if you take the red demand for the first column and add 3, you get this, and if you add 3 plus 2, you get 5, and so on. So there's this offset between the rows of the demands, and that's crucial for our algorithm. So suppose we know which rectangles were selected in this top region here. Maybe the first rectangle is selected and the other one is not selected. Then, of course, we already have covered something of the yellow-orange demand. So the top rectangle, top job had processing time 8, so the rectangle has size 8. And in this hatched region, we still need to cover the blue stuff because we didn't cover any of it up here. And we need to cover well, part of the orange stuff because we already have covered some of it. So we have those resulting demands in the hatched region. Now the important information observation is that still there's this constant difference between the rows. So for example, let's have a look at the second section, second column. In the hatched region, we need to cover the red demand of 2. We didn't cover anything on the blue ray up here, so we also need to cover 5 in this region. And on this orange ray, it had originally 11. We already have selected 8, so we need to cover 3. And now the important observation is that those 3 rays here, they all intersect with the same rectangles in the hatched region. So instead of keeping track that we need to cover the 3, the 5, and the 2, the only important thing is to cover the 5 because it's the biggest and they intersect with the same rectangles. So if we cover the 5, we are also fine with the other 2. And now we already observed that the blue demands are always differ by a constant from the red ones. So instead of keeping track of all of those demand rays, how much we covered on them, or keeping track of which rectangles we selected, we just remember that we need to cover the red demands. And on each of the red rays, we need to select rectangles which have +3, not only the demand of the red ray, but the demand of the red ray +3. That's like the new demand that we actually need to cover also the blue and the orange ones. And the important observation is that this is just one number to keep track of all the rectangles we selected above this hatched region. And thus, instead of remembering where we selected which rectangles and so on, we just tell our dynamic program in this region, okay, select rectangles to cover all of the red rays. And on each of the red rays, you need to actually cover 3 more for the above problem. So a cell in our dynamic program corresponds to some hatched area. And we have this additional value +f, which is the 3 from the last slide. And on the rays ending in the top row, we need to cover them plus additional 3. And so this region we allow for our DP can look like this. There is always a certain number of rectangles in the first row, so it can also look like this. Or it can also contain multiple rectangles in the first row. In this example, we have 3. Because in general, we are only interested in, so there are different types depending on how we got there, because we cannot really change it. And if we now want to solve our original problem, we can just look at the whole area and choose f equals 0. So we can select all rectangles and we cover all rays and we are fine. Now let's have a look at how we actually recursively can solve this problem. First of all, if there are multiple rectangles in the first row, the recursion is very easy because we can just split it in a left and a right part. And if we had additional f, we now have additional f values for both of the subproblems. So this recursion is very easy, and always if we have more than one rectangle in the top row, we can just split it in a left and a right part. And of course this works because we have this very cool structure of the rectangles because they are aligned. So if there is an end of a rectangle, also here we can split it up into 2 disjoint regions. The other more interesting case is when we have only one rectangle in the top row. In this situation, we cannot split it up into a left or a right part because we need to cut rectangles and that doesn't work. So we want to recursively have a look at the region just below it where this one rectangle is actually missing.
And we want to compute this solution by using the one for the yellow hatched region here and this one. So there are basically two cases. Either we select this rectangle here or we don't select it. And no matter whether we select it or not, we need to use a matching solution for the bottom one. And I already said that for the Blu-ray, we have this additional demand in our DP cell, which says that on the Blu-ray, you need to cover the blue demand plus F. So now let's have a look at the region below. And we want, instead of, so if we have this additional value for the blue demand, we want to transform this to an additional value for the orange demand, because in this region they are the same. So if we select this more on this Blu-ray, we also need to select more on the orange ray. That's basically the idea. So let's compare the blue and the orange demand. And I put back the images, how we constructed the demands. So we took all rectangles that were released in this interval, all jobs without the red one. And we looked how much of the jobs is left after T. So that's the blue demand and that's the orange demand. And if you look at this image, of course, the difference between the demands is just this. That's the difference. Or because you can see those are just the same jobs here, you can also see it at the difference between this time moment and the time moment we finish the light blue job. That's the same difference. And it turns out that if you look at this one, at this endpoint of this, so this endpoint of the light blue rectangle, that's not depending on T because it's just the start time of the interval plus the length of this job. And also this time moment doesn't depend on P. So the difference between those demands is not depending on T. And that's exactly the observation we had in the previous slides where we actually computed the numbers of the demand. We also saw that the difference between the demands doesn't depend on T. Now, the idea is that if we need to cover, suppose we didn't select this top rectangle, then we said we need to cover the blue demand plus F. And the blue demand plus F is just the same as the orange demand plus this difference plus F. So for this hatched region, we have a new F value, which is different from this one, of course, and it's just this plus this difference. And because this difference here is independent of T, that actually works. So we have only one F value for the whole region, and as this is independent of T, we can just add it to F to get the F value for the whole region. And so the crucial observation for our dynamic program is that this difference in the demands is independent of the time moment when the intervals actually end. And of course, if we select the blue rectangle, then we just reduce F by the size of this rectangle or by the processing time of the first job, and then add again this here to get the demand for this region. And those are the two options for the recursion we actually need in our dynamic program. So with this dynamic program, we can find an optimal selection of rectangles, and that's the best we can do, of course. So in the end, we observe a PTAS for the original problem. So let's have a quick look at what we actually saw. We started off with this weighted flow time scheduling problem. And as we used the reduction from the previous paper by Rohwedder and Wiese, which only lost a factor of 1 plus epsilon, although I explained it at a different setting, but the reduction here is quite similar. And then we used the dynamic program to solve this. And also the dynamic program, instead of one additional value, you get a constant number of additional values for each of the intervals if you apply it to this more complicated geometric covering problem. But more than that doesn't really change. And as you remember, we had this F value, which is not polynomial bounded by the number of jobs, but by the processing time. So our algorithm is pseudo-polynomial. but by the result of Feige, Kulkarni, and Lee, we can turn it into a polynomial time running algorithm, which then results in a PTAS for this problem. Thank you.